Welcome to Section 8 of Biostatistics. Recall that in biostatistics, we can break it down by first performing the studies, evaluating the studies, and then applying the study clinically. In this lecture, we are talking about applying studies by focusing specifically on incidence, prevalence, and likelihood ratio. So let's get started. The incidence of disease is found by taking the new cases during time X and dividing that by the population at risk. Something to keep in mind is that patients that are diseased prior to time X are not at risk. They already have the disease. And incidence is found in cohort studies. Prevalence is found by taking the total number of cases and dividing that by the population. Notice that we are not looking for a time frame in prevalence like we were in incidence. And prevalence can be found in cross-sectional studies or ecological studies. Now let's say we are trying to find the prevalence and incidence of AIDS in a population of 300 people. To find the prevalence, we merely count the number of AIDS patients at any single point. And let's say that the point in which we are looking for prevalence is time A. And at time A, there are 3 AIDS patients in this population. So the prevalence of AIDS is the total number of cases divided by the total population, which is 3 divided by 300, which is 1%. Now let's find the incidence of AIDS in this population. Recall that to calculate incidence, you need a time frame. So let's say that our time frame is from time A to time B, and let's say that's 1 whole year. And recall that incidence equals new cases divided by those at risk. And during this time frame, during this year, we find 1 new case. So the numerator is 1. However, at the start of this year, at time A, we had 3 AIDS patients. These 3 patients are no longer at risk of getting the disease because they already have it. So our calculation would be 1 divided by 300 minus 3, or 297. And this gives us an incidence of 0.3%. Now let's relate prevalence to sensitivity, specificity, likelihood ratios, and positive predictive values and negative predictive values. In Section 7, we discussed in detail that as prevalence increases, the positive predictive value increases, and as the prevalence of the disease decreases, the negative predictive value increases. We won't spend any more time on this idea in this video. What I would like to draw your attention to is the important fact that prevalence does not impact sensitivity, specificity, or likelihood ratios. This is an important fact to remember, so let's apply it with a question. Let's say a woman is told by her physician that she may have disease M. However, the physician warns that the test used to diagnose disease M does a very poor job of catching all the diseased patients. Even with this knowledge, the woman would like to have the test performed and claims that the disease is now more common in her community. If the disease is more common in her community, what impact would this have on the probability of the test coming back positive if she has disease M? So we are talking about a hypothetical disease called disease M. The doctor states that the test for diagnosing disease M does a poor job of catching all of the diseased patients. In other words, if you have the disease, the probability that your test will be positive is low. So what does this describe? Sensitivity. The woman states that the disease in her community is now more common. In other words, it's more prevalent. And the question was asking us if the increase in prevalence will end up altering the probability of her getting a positive test if she has the disease. In other words, will higher prevalence alter the sensitivity? The answer is nope. Recall that prevalence impacts negative predictive value and positive predictive value, but prevalence does not impact sensitivity, specificity, or likelihood ratios. So now let's talk more about likelihood ratios. Positive likelihood ratios, which you will see as LR positive, tells you how much your probability of disease shifts up if the test result is positive. Ideally, a positive likelihood ratio is greater than 10. And this means that a positive test result will increase your chance of disease by 10 times. Negative likelihood ratios, you will see as LR negative, tells you how much probability of the disease shifts down if the test result is negative. Ideally, a negative likelihood ratio is less than 0.1. And this means that a negative test result decreases your chance of disease by 0.1 times. As written here, is less than 10% of your current risk, because a multiple of 0.1 is 10%. Now, it's important to know that before likelihood ratios are calculated, you need the pretest probability. Pretest probability is basically what risk factors the patient has that make the disease a possibility. For example, when thinking of type 2 diabetes, an obese middle-aged patient has higher pretest probability than a teenage athlete. Next, it's important to know that all diagnostic tests have both a positive likelihood ratio and a negative likelihood ratio. And you want to calculate the positive likelihood ratio to evaluate the impact of a positive test. In other words, how would this impact your clinical decision making? Before, we mentioned that a positive likelihood ratio greater than 10 is valuable, and that's because it's high enough that it would impact your clinical judgment, so it's worth ordering. Conversely, a negative likelihood ratio will help you determine the impact of a negative test, should your patient's test come back negative. And as mentioned before, a negative likelihood ratio is ideal if it's less than 0.1, because this would impact your clinical judgment and treatment of the patient, so the test would be worth ordering. And if your positive or negative likelihood ratios would not change your treatment, don't order the test. So picture likelihood ratios being discussed and evaluated before the test is ordered. And you want to know both the positive likelihood ratio and the negative likelihood ratio for the diagnostic test. After all, the test could come back positive, or it could come back negative. With regards to the positive likelihood ratio, you want to know how much a positive test would increase the chances of the disease you're looking at. To see this visually, here is the math behind the idea. Pretest probability times positive likelihood ratio equals the post-test probability. And as you can see mathematically, if the positive likelihood ratio increases, then your post-test probability increases. In other words, a positive likelihood ratio will tell you how much a positive test will increase the odds of disease. Now, you are also aware that your test could come back negative, and you want to know how much a negative test result would decrease the probability of disease. So again, showing you the math, a low negative likelihood ratio would decrease your post-test probability. In other words, a negative likelihood ratio tells you how much a negative test decreases your odds of disease. Now let's relate likelihood ratios to sensitivity and specificity. Positive likelihood ratios are found by taking the sensitivity and dividing that by 1 minus the specificity. Negative likelihood ratios are found by taking 1 minus the sensitivity and dividing that by the specificity. However, it is vitally important that you recognize that likelihood ratios are determined by sensitivity and specificity. So it would make sense that likelihood ratios, like sensitivity and specificity, are not altered by prevalence. So let's do a quick example. So let's say we are evaluating test A, and the sensitivity is 90%, and the specificity is 95%. What is the positive likelihood ratio of this test? Well, recall that this is sensitivity divided by 1 minus the specificity, which comes out to be 0.9 divided by 0.05, which equals 18. This means that if you get a positive test result, the probability of having the disease shifts up by a factor of 18. Now let's find the negative likelihood ratio for test A. Recall that the equation is 1 minus sensitivity divided by the specificity. This would be 0.1 divided by 0.95, which comes out to be roughly 0.1. This means that if you get a negative test result, your probability of having the disease shifts down by a factor of 0.1, or 10%. So what does this mean clinically? Well, as a physician, if you order a test and if it comes back positive, it shifts the probability of disease up by 18, that's going to have a big impact on your clinical judgment and decision making. Likewise, if a negative test result shifts the odds of disease down to 10% where it would have been otherwise, this will also have a big impact on your clinical judgment. Therefore, whether or not the test comes back positive or negative, test A is a good test. Now let's compare this to test B, which has a sensitivity of 60% and a specificity of 55%. This would give us a positive likelihood ratio of 1.3, meaning that a positive test result would cause the probability of disease to shift up only by a factor of 1.3. That's not a lot. This means that even if the test comes back positive, it's not going to have a huge impact on how you treat the patient. The negative likelihood ratio would come out to be 0.7. This means that a negative test result would cause the probability of disease to shift down by a factor of 0.7, or down to 70% of what it currently is. And decreasing the probability of disease down to 70% where the pretest probability is not very dramatic, which means it doesn't make much difference. Which means, just like with the positive likelihood ratio, it's not going to make that much clinical impact. So whether your test comes back positive or negative, the test really isn't going to help your decision making all that much. So it's not a very good test. And I want to draw your attention to something very interesting. Notice that in test B, the sensitivity and the specificity were not as good as the sensitivity and specificity in test A. Test A had better and more significant likelihood ratios, and test B did not. And I draw your attention to this just to remind you that likelihood ratios depend on the sensitivity and specificity. Now let's relate likelihood ratios to positive and negative predictive values. I want you to look at both of these ideas side by side because they can be very easily confused, especially on a test. And as we learned before, likelihood ratios shift your probability. Positive likelihood ratio tells you that if you get a positive test, your probability of disease shifts up by X. And with negative likelihood ratios, if you get a negative test, your probability of disease shifts down by X. Contrast that to predictive values, which basically tell you your current probability. In other words, a positive predictive value will tell you that if you get a positive test, your probability of having the disease is Y. Likewise, a negative predictive value, if you get a negative test, your probability of not having the disease is Y. Let's plot out our 2x2 table, which gives us true positives, false negatives, true negatives, and false positives. Now let's fill in these boxes with numbers. As a review, the information in a 2x2 table, such as this, can give you a positive likelihood ratio or a negative likelihood ratio. It can also give you sensitivity or specificity, or it can give you positive predictive value or negative predictive value. To save time, the information in this box results in a likelihood ratio positive of 3.2, a likelihood ratio negative of 0.33, a sensitivity of 74%, a specificity of 77%, a positive predictive value of 84%, and a negative predictive value of 63%. Focusing on positive likelihood ratio, you can see that a positive test would increase your probability of disease by a factor of 3.2, while a negative test result would decrease your probability of having the disease by a factor of 0.33. Compare this to our positive predictive value, which indicates that a positive test means our probability of disease is 84%. And finally, negative predictive value, if we get a negative test, the probability of not having the disease is 63%. The point is that likelihood ratios and predictive values can both provide valuable information. They are merely asking different questions. So now let's do a question to tie this all together. Let's say an 82-year-old male with suspected acute myelogenous leukemia, or AML, is about to undergo diagnostic test F. So prior to suggesting this test to the patient, the physician studies the literature and finds that a positive test increases the patient's odds of disease, AML, by a factor of 11.3. However, a negative test indicates the patient's chance of not having AML is 0.8. What information was given by the values 11.3 and 0.8? Well, we learned that a positive test increases the odds of AML by 11.3. This is describing a positive likelihood ratio. We also learn that a negative test result indicates the probability of not having the disease is 0.8, or 80%. This is describing a negative predictive value. The point is that there are subtle differences in the wording of likelihood ratios and predictive values. But if you know what information each is providing, you will rock these questions on your exams. And that concludes this section.